What specific problem does the REVTHINK framework aim to solve in the context of reasoning with large language models? And how does it address the limitations of existing methods?
The REVTHINK framework aims to enhance the reasoning capabilities of large language models, LLMs, by instilling reverse thinking, addressing the limitations of existing methods that primarily focus on unidirectional reasoning. Current approaches, such as self-consistency and other test-time methods, show moderate improvements but are limited to mathematical tasks and do not train models to inherently reason backward. RevThink overcomes this by augmenting training data with backward questions and reasoning generated by a teacher model, allowing the student model to learn bidirectional reasoning through specific learning objectives. This method not only maintains test time efficiency akin to zero-shot prompting, but also results in significant performance improvements across diverse reasoning tasks, demonstrating greater generalizability and sample efficiency compared to traditional knowledge distillation and data augmentation techniques. Ultimately, REVTHINK's innovative approach enables LLMs to better internalize backward reasoning, leading to enhanced problem-solving capabilities in various domains.
How does the proposed method REVTHINK work? Illustrate the methodology step by step, detailing the data augmentation process and training objectives.
REVTHINK operates through a structured methodology that includes data augmentation and specific training objectives. First, it begins with a dataset of questions and answers, which is augmented using a teacher model to create a new dataset, D_August. This augmented dataset consists of 4 components for each sample: the original question, Q, forward reasoning, R_F, a backward question, Q_B, and backward reasoning, R_B. The forward reasoning is generated by the teacher model and is retained only if it leads to the correct answer. The backward question is formulated by reversing the original question, and the backward reasoning is derived by answering this backward question, ensuring consistency with the original problem. During training, the student model learns through 3 key objectives: 1. Generating correct forward reasoning from the original question, 2. Generating the backward question from the original question, and 3. Generating backward reasoning from the backward question. These objectives are designed to internalize the backward reasoning process, allowing the model to efficiently generate forward reasoning at test time, similar to zero-shot prompting. This dual approach of learning both forward and backward reasoning enhances the model's overall reasoning capabilities across various tasks.
Can you provide a specific example demonstrating how REVTHINK generates a backward question and backward reasoning from a forward question? Walk through the main algorithm steps with this example.
To illustrate how REVTHINK generates a backward question and backward reasoning, consider the forward question. John has 3 apples and Emma has 2. How many apples do they have in total? The algorithm begins by prompting the teacher model to generate forward reasoning, which would yield the answer: they have 5 apples in total. Next, REVTHINK formulates the backward question by reversing the original question, resulting in, if Emma has 2 apples, how many does John have? This backward question is generated by conditioning on the original question and the ground truth answer. Finally, the teacher model is prompted again to provide backward reasoning for the backward question, which would yield, if Emma has 2 apples, then John must have 3 apples. This process ensures that the backward reasoning is consistent with the original question, thereby augmenting the dataset effectively for training the student model.
What are the theoretical or practical benefits of using REVTHINK over traditional reasoning methods in language models? How does it enhance sampling efficiency and generalization?
REVTHINK offers significant theoretical and practical benefits over traditional reasoning methods in language models by instilling reverse thinking capabilities, which enhances both forward reasoning and overall performance across diverse reasoning tasks. Theoretically, it introduces a bidirectional reasoning framework that allows the model to learn from both forward and backward reasoning, leading to a more robust understanding of problem solving. Practically, REVTHINK demonstrates improved sampling efficiency, as evidenced by its ability to outperform the symbolic knowledge distillation (SCADE) method even when trained on only 10% of the data, showcasing its effectiveness in low-resource scenarios. Additionally, REVTHINK generalizes well to unseen datasets, achieving superior performance on out-of-domain tasks, which indicates its adaptability and robustness in various contexts. Overall, REVTHINK not only enhances reasoning capabilities, but also ensures efficient use of training data and better generalization to new problems.
How is the effectiveness of REVTHINK validated? What experimental design, datasets, and performance metrics were employed to showcase its improvements over other methods?
The effectiveness of REVTHINK is validated through a comprehensive experimental design that evaluates its performance across 12 diverse datasets, including common sense reasoning, mathematical reasoning, logical reasoning, and natural language inference. The models used for evaluation are Mistral 7B Instruct and Gemma 7B Instruct, with performance metrics focusing on average percentage improvements over the student model's zero-shot performance and comparisons against baselines such as symbolic knowledge distillation, SKD, and various data augmentation methods. Results indicate that REVTHINK achieves an average gain of 13.53% over zero-shot performance and 6.84% over SKD, demonstrating its superior performance across all datasets. Additionally, REVTHINK exhibits strong sample efficiency, outperforming SKD even with only 10% of the training data, and shows consistent improvements as model size increases. The method also generalizes well to unseen datasets, achieving notable performance gains in out-of-domain evaluations, further validating its effectiveness.
What limitations or drawbacks does the REVTHINK framework have, especially regarding its applicability in various domains or problem types?
The REVTHINK framework exhibits limitations primarily in its applicability to less structured domains and specific problem types. While it demonstrates significant improvements in structured reasoning tasks, such as pre-algebra and pre-calculus, it shows no substantial gains in areas like number theory, which are less invertible and do not benefit from backward reasoning. Additionally, the framework's reliance on the teacher model for generating backward questions and reasoning may introduce distributional shifts that could hinder performance if the backward questions are not fully in-domain. Furthermore, the effectiveness of REVTHINK diminishes in problems where the inverse relationship between questions and answers is weak, indicating that its advantages are context-dependent. Overall, while REVTHINK enhances reasoning capabilities in many scenarios, its performance may not generalize well across all reasoning tasks, particularly those lacking clear invertibility.